recording for Tristan. Okay. He just has it's the same amount of time you guys have. He has to study hall.
But he hasn't actually reviewed, but he doesn't get that.
Are we going to be putting out some properties?
Yes, ma'am. Getting your pens ready? All right, so we have the product rule for derivatives, but the anti-product rule for integrals doesn't exist. And so we need a process called integration by parts. Okay, anti-product rule for integrals is non-existent. But we can take the product rule and we can develop the integration by parts. So the product rule says this: d dx of a uv product, and we know that the product rule says that you do this. You take v times du dx, and then you add it to u times dv dx. That's the product rule in its pure form. Let's clear out the fractions. So what is the fraction here? Dx. And so multiply everything by dx. And so we end up with duv v du plus u dv. Okay. So we've started with the product rule. We've eliminated the fractions. And now we're going to put an integral on each piece. So we're going to put an integral here, and an integral there, and an integral there. On the left side, the integral comes in contact with the d, which stands for differential. And what do those two do to each other? They cancel out. So what am I left with? uv. The other side, I don't have that happen because only one of the parts has the differential on it, not both. So it stays the integral of v du plus the integral of u dv. And what we want to do is isolate one of the integrals so that you don't have both on the same side. And so it wouldn't really matter which one you did, but we'll just try and stay consistent with the rest of the world. And the rest of the world has decided to isolate the u dv part. And so what do I do to the other integral? I subtract it. So I end up with uv minus the integral of v du. That format that you end up with is what is called integration by parts. And that truth, that property, that you can isolate one integral and end up with the subtraction on the other side, is what is called the process of integration by parts. So the parts are that there's a u and a v and a differential on both of them. So those are the four parts of the problem. When we say integration by parts, this is what we're talking about. The four parts are: there's a u and a du part, and there's a v and a dv part. So there are four parts to the integration by parts. And so instead of just assigning a u substitution, we're going to assign a u substitution, but we're also going to assign a dv substitution also. And so it's taking u substitution and it is taking it a step further to allow you to do more of an integration. And so we will be assigning these two parts first. The u and the dv parts will get assigned first. Now, choosing your u, that's where I refer to the Lippitt test. All right, choosing your u, L-I-P-E-T, is an acronym that helps you prioritize what's going to be the best u based on the type of equation that you're given. So L stands for a logarithm. If any part of your problem is a logarithm, that'll be what you choose for u. I stands for inverse, and it's specifically an inverse trig. If you don't have a logarithm, then you look for an inverse trig. If you happen to have one of those, that'll be your u. P stands for polynomial. So if you don't have either of the first two, but you have a polynomial, like a squared or a cubed or something, that would be your next choice. E is an exponential function. And T is a trigonometric, which would be the last choice. It might make sense to you that a trig is the last choice, because if you choose a trig for your u, it just keeps cycling back and forth on top of itself, right? You go from sine to cosine, back to negative cosine, back to positive sine. So we really don't want to, if we can avoid it, we'll not choose the T for trig. So this all has to do with what you choose for your u substitution, and then everything else that's left would become the part dv. So you assign u first, then assign dv, and then you'll be able to figure out the other two parts. Sometimes you'll see people arrange it in like a little box, and they'll put the u part here, and they'll put the dv part, and the v part, and the du part, or they'll put their parts in some kind of organizational strategy just to help them out. It's up to you. You may do that if you like, but you might see a future professor or a future book or something, you know, assign the parts into boxes and then just help themselves go. That property that I put in the green box at the beginning, I'm just going to flip-flop it so that it's easier to work with. I'm going to put the single part of the UDV on the one side, because that's usually the order when we work from left to right. So we'll be working in that part. We're going to start with assigning a U, and we'll also assign a DV. Once we have that, then we'll be able to move forward with the UV combination minus VDU.
Is it only that, or can you also do the integral VDU?
Yeah, sure. You could do the other way. It would totally work. I'm just going with what's conventional and what most people, you know, just so it's consistent with choose a U. It sounds like the U substitution. I could have said choose a V,
Okay.
And that would have been fine as
So
well.
all of our problems, will it be a DU every time? I mean, a U and a DV?
Yeah, I think that would be the most consistent. Yes. All right, so let's try one. Yeah. Yes. X is a polynomial. Linear is a polynomial of degree 1. Yes.
Where does where you go?
Say that again?
Where you
Uh-huh.
shouldn't it be U, D,
You can do that in that order too. Yep.
Okay.
Yep. Some people like to arrange it this way because they do it kind of in the order of how they assign it. Like they'll pick this first and they'll pick this second. They'll figure out this third, they'll figure out that fourth. And then when setting up the second half of the problem, they do a combination of those two together and then a combination of those two together. And so, you know, it's just a strategy that you could try, but you don't have to do it that way. Okay, so let's actually try one. So this is going to happen when you have a product where regular U substitution doesn't work. Okay, try regular U substitution, but what's going to happen is that the reducing isn't going to happen like you were maybe expecting it to in the past. Okay, so here we go. X sine X. It's a product. U substitution isn't going to work. I'll show you why. You assign your U using the Lippitt test. There's no log, there's no inverse, so that's a polynomial, and so X would be the first one. So then the du would simply be dx, and that's your first clue that regular U substitution doesn't work because there's nothing to reduce out the x. So that's your first clue. All right, so it's not going to be regular U substitution, so I'm going to get rid of that. So first I assign my u, then I assign my dv, and my dv is everything else in the problem that wasn't u. Everything. So my dv would be sine of x dx. So if those are the two things that I've chosen, now I should be able to figure out what v is, and I should be able to figure out what du is. Well, du is diagonal from regular u, so du would be the differential on that, which would be x. dv is diagonal from what v is, and if dv is sine of x, then what is regular v?
Negative cosine.
Very good, negative cosine. So do you see how in one direction you're going derivative, but in the other direction you're going antiderivative? Okay, so then maybe you want to do this, I don't know, make a box, whatever. So what you're saying is that the original function, the original problem, which started out as x sine x dx, is equivalent to the following combination. It's equivalent to the combination of uv, think like UV rays, you know, like you put sunscreen on to protect your UV rays. Okay, you start with uv, so the uv would be negative x cos x minus the integral of what you ended up figuring out v to be and du, which is negative cos x dx. So you got a double negative now going on there. So we'll make that a positive. And the integral we end up with is an integral that is workable. We know the antiderivative of cosine of x, and so we end up with negative x cos x plus the perfect antiderivative of cos, which is sine, plus the constant c, and that's the answer. So we ended up with a, yeah, Bobby? Okay, so we ended up with a product whose antiderivative is a sum of two different terms with a plus c on the end, which you can always check by taking the derivative and going back to do the derivative again and making sure that you ended up with what you started. Yeah?
So this method applied to the definite u.
Yes.
We change the bound.
Okay, so if you had a bound, no, you don't have to change your bound. If you had a bound a to b, I'm going to do one of those sample problems in a minute, but if you have a bound a to b, you do all of the antiderivative work, and then when you get down to your plus c, you're going to put your a, b here and just plug them in and keep going from there. Okay, but you don't have to convert any of your bounds. Okay, all right, let's try again. Okay. All right, let's do the integral of x times e to the negative 2x dx. Okay, and again, this is a product whose regular use substitution doesn't work. And so using Lipit, we want to assign L no logarithm, no inverse, but there is a polynomial, and so u is x again. Which means everything else is my dv. So dv is e to the negative 2x dx. Which means now I should be able to figure out what v is. So v is the antiderivative of e to the negative 2x dx, which is e to the negative 2x over negative 2. And then du is simply dx again. All right. So then we're ready to proceed once we have our four parts. So the original problem, x e to the negative 2x dx, can be simplified or replaced as equivalent to uv, which is x times e to the negative 2x over negative 2, minus the integral of v du. So e to the negative 2x, which is already over negative 2, followed by simply dx. So again, I've got a double negative, which I make positive. So I have x e to the negative 2x over negative 2. And then the antiderivative of e to the negative 2x will be e to the negative 2x again, but this time what's it going to be divided by? Negative 4 plus the constant c. Okay, any questions on that so far? I had my original two negatives to make a positive, and then I'm going to do the antiderivative again. I'm going to divide by negative 2 one more time.
Oh, okay. So shouldn't you just...
So I had 3 negatives, yeah. So I could, if you would like, I could make that a positive and make this a subtraction. Doesn't matter, like that. Okay, let's try another one. So in both of the cases right here, when I got to my second integral form, what was I able to do with that second integral? I could solve it. What if I can't? Then you gotta do it again. Okay, so x squared cos x dx. A product, which needs the limit, integration by parts. So skipping the logarithm, skipping the inverse, and jumping right to the polynomial. The polynomial is going to be x squared, which means my dv is everything else. So dv is cos x dx, which means my v had to be sine x. My du is 2x dx. You could, yeah, you'd get a, yeah, yeah, I guess. If you recognized right away that you were going to have to do it again, I suppose you could do it again. Then your u this time would be 2x. Your dv would be sine x 2x dx, I mean. So v is negative cos x and du is negative 2 dx. You want to do it like that? I guess that's okay. I hadn't thought of doing it that way. Just doing it right away. Oh, no, positive, positive, positive. The regular way?
Skipping like 2 or 3.
Yeah, we just skipped 2 or 3 steps, yes. All right. I was tracking with you, Jerry. I know what you were doing. Okay, so we're going to set this up. So we've got the integral that started out as x squared cos x dx becomes uv, so x squared sine x, minus the integral of v du, which is 2x sine x dx, which requires integration by parts again. So that was what I was doing a second time, is I was setting that up again. Okay, so I'm just going to slide all my notes over, and I'm going to do it again. So my u still has to be the polynomial, so it's 2x is the polynomial, which means dv is the sine x 2x, which means v is negative cosine, and u is 2 dx.
Wait, du?
Do you, yes. Good girl, good catch. No, 2 dx, I was right, because it's the derivative of x. 2x.
Well, what about du? Where's du?
Oh, yes, yeah. Okay, so then we'll just group these. And so we'll have this uv, which would be negative 2x cos x, minus this integral, which would be negative 2 cos x dx. So double negative there. Okay, but what's in front of what I just did?
Oh my gosh.
The two things that were in front of that. So it's x squared sine x minus, and then maybe put a bracket around all this or something, because that minus is in front of both that whole thing. But that second integral we can do now. So I'm going to distribute my negative. So this becomes a positive, this becomes a negative. I just distributed my negative. Okay, my negative got distributed. So my final answer is x squared sine x plus 2x cos x minus 2 sine x, and then plus c as a constant.
Are we expected to see a problem like this in our?
Mm-hmm.